Okay, I'm just going to talk about some tips for evaluating W integrals on rectangles. So kind of the easiest geometry to work with. They vary in complexity. I think the easiest example, given our rectangle, I think the easiest example is products. Like if you see this, you just jump up and scream for joy because this is just simply f of x, g of y, dy, dx. And this is not integrated, this is a product. So if there's a product here, product of functions, you get a product of integrals. And the reason is that if you use Fubini to do this iterated style, you can just pull this thing outside because remember, we're freezing x in the y integral. And then you just do it again. You just take this number, that's a number now, outside. So now you have the integral of g times the integral of f. Right, so for example, if you do xy, like we did it last time, we just iterated, but you can actually just split it up like this. And so you get 1/4, like, and that's how we got it before, but it's a lot quicker this time. Actually, this idea, it's one way to evaluate the famous Gaussian integral. And we'll probably talk about that when we get access to polar coordinates. So I won't go mention that further. Another tip. I'm just going to go ahead and call this tip 1, products. The second tip is for when the integrand looks complicated. So if you have a complicated integrand, look for a trick. So the first trick I'll mention is exact derivative. Like, for example, if we have something really nasty, like cosine of xy, that could get kind of messy if you start to try to do the y integral. So for example, if we try y first, if we try doing y cosine xy dy, and whatever the y range is, then this requires integration by parts to do. So that's hard. So the easier way to do it is just to notice that y cosine of xy is actually equal to the partial derivative of sine of xy. So in other words, you do a u substitution in x, right? So you let xy equal u. That means that du is y dx. So that takes care of this extra y out here. Okay, so if you do that, then what you get is cosine of u du dy. And so now you have the integral from, let's just say, it's 0 to 1. Now the integral is 0 to y. So we get a slightly more complicated looking integral, but now you don't have to use integration by parts. Now you just get sine of y dy, and that thing you can do. So the upshot is look for extra y's, and it implies that they come from the chain rule. And then that allows you to do u sub. So another tip you can use is look for symmetry. So oftentimes an integral will simply be 0 because, for example, if we look at just x on a symmetric interval, it's an odd function, the negatives cancel the positives. And so we get 0. Well, the same kind of thing can happen. So they might give you something really complicated, a really complicated expression, and it turns out this is actually just 0, just because it's of symmetry. So what about something like xy over 1 plus x to the 4th dA, and we're going to integrate it on this rectangle here. Well, it's pretty bad looking integral because this part, I'm not sure there's actually an antiderivative for that. However, the y part is pretty good. It is antisymmetric on a symmetric interval. So I would just look at this situation, and then you can see that this is 0. And what about another example? If you look at 1 plus x squared sine of y, see it's looking complicated, so you should see that there's a trick going on here. Then you put a dA here. You see, wow, oh my god, that is so complicated. I'm going to have to spend an hour doing this. But that should tell you there's a trick. And the region is also important. So the region is given by minus pi to plus pi, and minus pi to plus pi, and it's the square here, right? So it's a symmetric region, and we have sines. Remember, if you look at the sine graph, it's an odd function. So this is odd. This is odd. So actually, these things go to 0. So that means our integral just evaluates to this thing. So it's just the area of the region. So it's pi squared. Oh, not pi squared. 2 pi squared. Okay. So the more complicated the integral, it should tell you that there's some sort of trick you should look for, because they will not give you I say they like WebAssign, but really it's me also. They will not give you an unsolvable integral. Okay, so there's always a trick. It's either going to be a U sub, or it might be symmetry. In the easiest case, it'll be a product, or it could be just a straight up iteration. And you just have to crunch it out.